All right, so this is me and my group's project 3. I'm Sean, and I'm working with Sarah and Kevin here. Here's our problem statement. We decided to go with the first problem for this assignment, uh, with the ball and the pendulum. Oh, wait. A ball with a mass m1 is suspended from the ceiling and released from rest. After swinging down, it collides elastically with the second ball of a mass m2, which hangs vertically on the string of the same length L. And we're asked to calculate the maximum height each ball reaches post-collision. And then here's some of our assumptions. We have an ideal rope, particle model, near Earth surface, energy is conserved, momentum is conserved, and it ignores air resistance. Only potential and kinetic energy, and there's no thermal. And here's a little example of what it would look like if the balls had the same mass. Just found this on YouTube. Kind of counteract each other. Okay.
All right, so in the equations that we are going to show you in the soon, we're going to have some variables for each of our masses. So M1 is going to be the mass of the mass of ball 1. M2 is going to be the mass of ball 2. L is going to be the length of the string for both of them, and we know the length is going to be equal. Theta is going to be, theta is the angle of the rope on the top. P is going to be our potential energy. G is going to be gravity like always, and H is going to be the height of the ball. And we wrote a little energy system. And so we included Earth in our energy system, and it affects both of the balls. So for ball 1, M1, there's gravitational potential energy, and it's going to be converted into kinetic energy. Same for our M2, we're going to have kinetic and gravitational potential energy. And
Okay, so for calculations, we did some basic trig to first determine the height of M1, ball 1. And after finding the height of that, we can plug that back into the potential energy equation to find H. And here we have a little bit of calculations for that. And then on this page, the problem says that the collision is elastic. And so that means that momentum and energy are conserved, which means that the total momentum of the system before the collision is equal to the total momentum of the system after the collision. And that's the same for energy. So on the left, the bottom left here, we have all the steps that we did. So we started with finding potential energy for mass 1, and then the potential energy for mass 1 equals the potential energy for the kinetic energy of mass 1 right before the collision. And then for step 3, we have conservation of energy for potential energy. So the 2 initial potential energies equal the final 2 potential energies. And then step 4, we have, again, conservation of energy, but this time for kinetic energy. So the 2 initial kinetic energies equal the 2 final kinetic energies. And then after we find those, we solve for VF1 and VF2 using the potential energy and kinetic energy that we found. And then for step 6, we can say that potential energy equals kinetic energy and solve for H. So on the right here, you can see all the calculations that we did. There's some algebra steps that aren't written down. That would be so much to see. But we found at the bottom our H2 and our H1. And then, so start off our sense make, we did units. And so we know that H needs to be in meters. And so for both our masses, those are both kilograms, gravities, meters per second squared. Again, mass is meters, and then those all cancel out, and you're just left with meters equals meters, and that checks out. And then that's the same for H1 at the bottom and H2 at the top.
All right, so for sense making again, we like earlier in the video that you saw earlier when two balls have the same mass, the one that's going down and the one that's at rest, when it goes down, the one initially at rest moves, but the one that was coming down stops and has a height of 0. So we tried sense making this. So we had our M1, the ball that's coming down, 2 kilograms. We had M2, the ball at rest, also 2 kilograms. We had our L 1 meter. So it's very simple calculations. Same with theta. We had a 45, which is a generic fall. And gravity obviously is 10. And so for our calculations, we got for the ball 1, which is H1, we got 0, which matches up with the video that you guys saw earlier, so that when it comes down, it initially stops while the other one goes. And for height 2, which is the ball 2, we did get a height. And so we did another sense make where we kept everything the same. Our constants was the length between the length of the string. Theta was also 45 and gravity was also 10. But the only difference this time was that we made the ball that was coming down M1 greater than the ball that's initially at rest, which is 2 kilograms. And so for our calculations, we got that the height of ball 1, the one that's coming down, doesn't have as high of a height as the ball 2. And this also makes sense because the heavier ball does not travel as high as the lighter ball, which is, I mean, if you do anything with in the real world, you have a heavier object, it clashes against a lighter object. Obviously, the lighter one is going to move farther. And for our extreme cases, we had both mass 1 and mass 2 different weights. And then obviously we got L 1 meter as well for simple calculations. And for these extreme cases, we had our theta value at 90 and at 0, so 0 and 90. And so for our extreme case of 90, we had our ball 2 initially at rest, having a higher height, while the ball that's coming down has a lower one. And we did for another extreme case, we had the same exact weight for both the balls, same exact length, but this time our theta value is 0, so both balls are just right here. And for here, we got that both the heights of the ball were 0 because, I mean, if there's no theta, there's no motion going down, they're both just still right there, so they have a height of 0, and yep.
Okay, so to wrap it up for the reflection, how was our group successful this week? We found 2 times that worked for all of us and met at the library. We met Wednesday and Thursday. We tried to knock it out a little earlier than last time, and we worked efficiently while incorporating everybody's ideas into our slides and work. And so what mistakes did you make this week, and what steps will you take to improve those mistakes in future projects? Yeah, we did better on our meeting time, and we still could have met like a little earlier. Wednesday and Thursday are still also kind of rushed. So to future groups who are doing projects, if they're like in 212, make sure to like try and meet like a week before. It takes a lot of stress off the shoulders, and like you're just in less of a rush, and you can look at the problems more thoroughly. And then what activities did you do from this week that were similar and different from this activity? And I said in Studio 10, we had a problem for activity 10.4, the angled ramps one with the 2 pulleys with the frictionless ramp with the 2 blocks on the side. It was really similar to this one. We had unknown angles, and the only difference was we had to find the speed instead of the height. And they both involve ideal ropes at an angle, which can be tricky to work with sometimes. And they both needed working with energy diagrams or force diagrams, or like both depending on the problem. And so that's where it kind of related in class today. And yeah, that's it. Thanks.